Hello, my name is Jun. In this tutorial, I will explain the marching cube algorithm with the GPU on Unity. This algorithm can visualize some scalar field into the shape, which is called isosurface here. So with this algorithm, you can customize the mesh into whatever shape you want. You can generate geometry formation like valley, or mountain, and by comparing to voxelizing, this algorithm generates more smooth surface than voxelizing on the same resolution. And this is the parallel algorithm, so you can divide execution into the pieces, and each pieces are totally independent to each other, which means by that this algorithm is just good to work with the GPU. So as you can see here, this is one of the results of the marching cube algorithm. This is the toots. So let's get in. This program was used in my first project of my first company. It took me about 2 months for figuring out all mesh customizing algorithm and the graphic programming. And for some reason in my company, this project was stopped. But anyway, this is the project that I've learned marching cube and voxelizing and GPU programming. So let's check the short video that I filmed for this tutorial. So in the first screen, you can decide the resolution of the the marching cube. Here it's gonna be the resolution of these toots. So I'm moving this tool with just keyboard, and as soon as this small pin on the motor touch these toots, you can see it's actually carving these toots. And next here, this is kind of overall result that you can check what you did. So here you can check you kind of carved too much and where you carved and something like this. And going to next stencil, you can check the different shape. All these results are made by marching cube algorithm. So first, there gonna be abstract explanation, and later you can check the detail in the code. So let's say we want to get the marching cube result of this object, and then first we have to create the voxels. So all these voxels are created and aligned by the GPU simultaneously. So these voxels are aligned along this uniform grid of the object, and each this voxel is the structure, contains a position and scalar value, and this scalar value affects the actual shape of the result. So with this arrangement of these voxels, this divide the space into the number of cubes, and then now we are ready to use the marching cube algorithm. So for each cube here, we execute the marching cube algorithm. So the process is gonna be like this. So we execute our marching cube algorithm for each cubes, and the shape for each cube is different because the difference value, scalar value of the voxels for each cubes. So the final result is gonna be like this. And I want to point out again that all this execution for each cubes happen simultaneously because we are using GPU. And now we can execute the marching cube algorithm for the cubes. So first we have to set this indexing convention. This blue index is for the corner, and this orange index is for the edge of the cube. So all this arrangement apply the same for all these different cubes. And you might wonder, why do we need this weird indexing? It's because we have to use this lookup table. This is kind of predefined two-dimensional array that you can easily copy from the internet. So this table takes the corner information that contains this information of 8 corner of the cube. So this is the 8-bit integer value. So this table takes this and returns some edge information that you use it for generating integer, the polygons inside this cube. And second, we have to check all these corners of the cube. So for this example cube, we have this corner which is inside this object. So we can make this corner information like this. So each position corresponds to this index number of the corner. And since we only have the third corner which is inside the object, we can make this binary number like this, which is 8. So this goes through the lookup table and we will get this edge information. So this indicates we have 3 vertex to draw. So we draw the vertex on this each edge information. And then we will get this polygon. And since this is just simple explanation, so I set each vertex, you can see exactly middle of each edge. But you can definitely implement the linear interpolation for each vertex. So for example, for the vertex for this third edge, this can change depends on the scalar value of this corner and this corner. And for this vertex on this second edge, this can change depends on the scalar value of this corner and this corner, and so on. And we will check the next example cube. So for this cube, this 7th and 3rd corner is activated. So we can make this binary tree, the binary number, and it goes through lookup table, and this will return this different edge information. So now we have 2 polygons to draw. So first one 7 to 3, 7 to 3. Second one 6 to 7, 6 to 7. So this indicates not only the vertex position, but also the order of the vertex for each polygon. So here the 7 to 3, 7 to 3, and 6 to 7. So now you can see you are watching the front face of these 2 polygons. And as you said, more higher resolution, you get more accurate isosurface. But of course, it would take more performance. So you need to set the proper trade-off between performance and accuracy of the result. Before going into the code, this is the brief structure showing what actually happened inside this CPU part and GPU part of my program. So for the CPU part, which is kind of Unity, this mono behavior script declare and define the buffers inside the CPU memory and pass the buffer to the GPU. So after this initializing stage, for the runtime, this buffer always stay inside this GPU memory so that this compute shader and vertex pixel shader can access the buffer directly. So for the GPU part, this compute shader execute algorithm and store the output in that buffer, and vertex shader, pixel shader gonna use that data for drawing directly. And I think this is ideal structure because this modification by compute shader and rendering by this vertex pixel shader is done just inside this GPU. I don't have to rely on this Unity module that much, which mean by that, so we don't have to move this big size buffers inside GPU memory back to CPU memory, which takes a lot of performance. So now we are in the code of CPU side. So this is the mono behavior script. It's called chunk, and it's define this two buffer that I said earlier. The first one is voxel buffer, which has voxel information. Second one is polygon information, which has polygon information that we're gonna draw. So first, just initializing stage. This goes through this kind of function. So this init field first. So this function just initialize all field that we're gonna use for our marching cube process. And second function is initializing voxel. Here we generate the voxels. So first we have to define this voxel buffer. So we allocate memory for this buffer, so that the number of elements in this buffer are going to be, of course, total voxel number, and the size of each element going to be this size of this structure voxel. When you get in here, it has a position and scalar value. So after that, we pass this constant value into the GPU, so that this GPU can use this information for generating and arranging voxels. This is a GPU manager. This is a global script. When we get in here, it managed the compute shader, and then it initialized all compute shader function so that we can call it in CPU side. And this line get information of the object that we want to draw. So we get the vertex information and install it into the buffer, and get the triangle information and store into the buffer. And this is the mesh information of the object that we want to draw. If we go into this function, we get this vertex information and triangle information from this mesh, and convert it and store this two information into this buffer, so that we can use this information into the GPU. So we pass this buffer into GPU again, and last we pass this voxel buffer into GPU, so that the GPU can store the information to voxel buffer. So after this code, this voxel buffer always stay inside GPU memory and never move again. And we display a dispatch init voxel. So this function called this init voxel compute shader function, and then this function will call this compute shader function inside this GPU. By using compute shader function, all these voxels are defined by different threads simultaneously. So each thread with this given particular index parameter define its own the property of the voxels. Back to the code, I said 1024 thread per one thread group. And first we have in this function we have to set position. We can get XYZ index of the voxel from this index parameter, and we can get position using these numbers and store it. And we have to get the scalar value of this voxel. So we go through this function and we decide whether it's inside or not. So this is just 0 and this is the 1. So this is the function that tell if this voxel is inside the object or not. This picture explains how that function works. And this comes from the fact that if you imagine you're inside some object and you look around any direction, and then only thing you can see would be the inside of the object. So first we shoot the ray to any direction. I'm going to take this voxel example. From this voxel we shoot the ray to this direction. And second, we get closest hit distance of the inside surface and outside surface, two variables. So for this example, there's a 3 hit point. So whenever ray hit any polygon of the object, so we tell, so this ray hit inside surface of the polygon, and here hit the outside surface of the polygon, and this two that is closest hit distance, and we have to compare these two values. So for this example, the closest hit distance of inside surface is shorter than the closest hit distance of the outside surface. So we can tell this voxel is inside the object. And I'm going to take another voxel example. So from this voxel, we shoot the ray to this direction. And we detect 2 hit points. So this is the closest hit distance of the outside surface, and this is the inside surface. And in this case, the closest hit distance of outside surface is shorter than inside one. So for this voxel, we can tell this one is outside the object. And the result gonna be like this after GPU goes through all these voxels. And next we go through this initialize material function. So in this function we get ready to use our custom shader properly. So first we define this poly buffer, and the number of element is like this, because each cube can possibly have up to 5 polygons in it, and the size of each element is like this, and this is a structure that contains one single polygon information, so 3 vertices and 1 dormer face. And we generate new material of our sample material. This contains custom shader in it, our custom shader in it. And we pass this constant value to our shader, and we pass this poly buffer as well. And then this last material, we pass it to this our mesh renderer component. And last, we generate new mesh that has this number of index number in it. This is same as this number of element of this poly buffer, so that our custom shader gonna work for all possible number of the polygon in this buffer. So, and we pass this mesh to our mesh filter component. We're gonna go through this marching cube function. So inside this function, we're gonna call a different compute shader function again. The first time it was for generating all edge voxels, and this time it's gonna execute marching cube algorithm for all edge cubes. And this is pretty simple inside this CPU side. So first we pass this resource buffer to the compute shader, and we just call this marching cube compute shader function. So each thread gonna go through their corresponding single cubes. This time, this given index parameter gonna also indicate the cube index. Back to the code. So first, we have to convert this cube index to voxel index so that we can access 8 voxel corner of this cube. So first, we have to get this XYZ index of current cube, and using this, go through this formula, then we can get this vertex voxel index. So using this 8 voxel index, now we can define this corner information that you're going to pass to lookup table. So check all the scalar value of each corner and stored its corresponding corner index to its 8-bit this integer, so that it can cover all this information into this one single variable. And after that, before we go to lookup table that for getting edge information, we're gonna calculate this this vertex information in advance. So for now, I set this interpolation just into the middle. So this each vertex lies on the middle of each edge, but definitely you can set some nice interpolation using this scalar value of both sides of this corner. And we clean this poly buffer before we set any vertex position in it. Now we are ready to use this lookup table. So this is the just one-dimensional array. The size is 256, which is the total case number of the corner information, and multiplied by 16, which mean by that, so each corner information have 16 information capability, because it covers from no polygon up to 5 polygons, which is 15 vertex, and plus this each edge information have at least one of -1 value, which means end of the information. So the numbers here inside this each row means the edge information from the different corner information. So let's take one example. So we start getting edge information from this point. So we get first polygon, second polygon, and third polygon. And as soon as we meet this -1, we get out of the loop, and with this information we can make 3 polygons inside the cube. So first we multiply this corner information by 16, so that it becomes the right format as the parameter of this lookup table. And this is the macro value. This is -1. So first we check if this returned edge information is -1 or not. If it is not a -1, that means you have at least 1 polygon to draw. So you go into this loop and get first 3 edge information and pass this each edge information into this vertex position array that we just calculated earlier. Then we get this lot 3 vertex. And we store this vertex into the poly buffer in its corresponding index position, and using this 3 vertex and cross product, we can get normal face of the current polygon, and we store this as well. So later the custom vertex pixel shader gonna access this poly buffer and render this polygon. And we increment this index variable so that we go to next loop and check if there's additional polygon to draw or not. So finally we reach this custom shader for rendering. Here we can access this poly buffer as well. So first in this vertex shader we pass this poly buffer information, which is 3 vertex and 1 normal face, to this geometry shader. So in geometry shader, using these 3 vertex, it forms 1 single polygon. And last, in this pixel shader, we just applied simple lighting on it. Then you can see the isosurface of the margin cube that we have seen before. So this is the end of the tutorial. I hope this video can help someone who try to figure out the margin cube. And I also leave the link below so you can download the sample project if you want. See you next time.